Hello, everybody. Welcome back. Today we are going to be looking at Unit 7.7, which is all about calculating equilibrium concentrations. And really, it's more than that. It's doing some of the heavier duty calculations involved with equilibrium. So get your calculators out and let's get started. All right, so what I have on this slide and the next slide is a set of steps on how to do these problems. And you can look at them if you like, but what I would rather do is skip ahead to a practice problem and work through it together. Okay. And there is a certain method that is very commonly used in AP Chem, and that's what's in red here. We're going to create a table of initial and final conditions, and that's going to help us solve pretty much any kind of equilibrium calculation. So let's look at what I call type 1 of these equilibrium calculations. Okay, so we're going to work through this problem together in full. Okay, so right off the bat, I can see that we are given a balanced reaction. And it says, in a certain experiment, 2 moles of SO2, 1.5 moles of oxygen, and 3 moles of SO3 are placed in a 1-liter flask. Okay, so right there, those, ladies and gentlemen, those are my initial conditions. Okay, and the next sentence starts at equilibrium, which implies that the previous sentence, those were conditions not at equilibrium. Okay, so this sentence says at equilibrium, 3.5 moles of SO3 were found to be present. Calculate the equilibrium concentrations of oxygen, SO2, and also calculate a value for K. So what I'm going to write on the next slide, okay, I'm going to work this problem out. I would really encourage you to also write everything that I do. And the first thing that I am going to do is just simply rewrite the balance equation. 2SO2 plus oxygen yields 2SO3. And this method that is really common is called setting up an ICE table. Okay, let me tell you what these letters stand for. I of ICE stands for initial. Okay, initial what? Well, that could be initial molarities. You can also do these problems with initial partial pressures. Because remember, guys, you can set up an equilibrium constant expression, products over reactants. You can set that up with molarities. You can also set it up with partial pressures. Okay, so I stands for initial. In this particular problem, we're going to be working with initial molarities. C stands for change, because they're not going to stay in the same molarities they are initially. And E stands for equilibrium, the equilibrium conditions. So let's look at what we can fill in and what we can't. All right, so I stands for initial molarities. And if you look at the first sentence in the problem, I am given moles of everything and I'm given the volume of everything. And I made this one relatively simple with a volume of 1 liter. So let's come back and fill in the molarities of these pieces. So SO2 has an initial molarity of 2 molar. Oxygen is 1.5 molar. And SO3 is 3 molar. So those are the initial molarities. C stands for change, and I'm not quite sure how they're going to change yet. Like, are these numbers going to increase or decrease? We'll come back to that. I like to draw a line in between C and E, because E is equilibrium. All right, let's see what we know, if anything, about the equilibrium conditions. Okay, look at the second sentence in the problem. At equilibrium, 3.5 moles of SO3 were found to be present. Okay, well, we're in the same container, the 1 liter flask. So at equilibrium on the E line, we're going to have 3.5 molar right there. Now, if you will notice, guys, the molarity of SO3 increased. It went from 3 molar to 3.5 molar. So I'm going to put a little plus sign here, meaning that whatever the change that occurred there, it increased. Now, what does that mean for the reactant side? Well, guys, remember back from just the last lesson that we looked at. If I can see that based on my initial conditions and my equilibrium conditions here, that I acquired more product. We went from 3 to 3.5. That must mean that what happened to restore equilibrium was this reaction shifted in the forward direction, which means my amount of product has increased and my amount of reactants has decreased. Okay, now by how much? Well, I'm not really sure yet. Now watch what I write here. Under oxygen, I'm going to write minus X. Oxygen's molarity is going to decrease because I know this reaction is going to shift away from the reactants to consume some of them, but I don't know by how much, so I'm just going to call it X. Under SO2, I'm not going to write minus X, I'm going to write minus 2X because of that coefficient right there. However much oxygen is going to decrease, SO2 is going to decrease by twice that amount. And then over on the product side, SO3 is going to increase by 2x. Okay? And our job, ladies and gentlemen, is to solve what are the equilibrium molarities of these two pieces here. I know SO3. Well, look at what you have right here. 3 plus 2x equals 3.5. Let's pull that out to the side. Let's do a little algebra in our heads. If you can, you don't even need a calculator, hopefully. If you can do that math in your head, you'll see that x is equal to 0.25. Well, if you now know what x is, let me erase these circles here. We can plug x in right there and solve for these equilibrium molarities of SO2 and oxygen. And again, I don't think you'll even need a calculator. So for oxygen, 1.5 minus the value for x that we found, 0.25. Here's oxygen's final molarity. And SO2, I'm going to plug x in right there. 2 times 0.25, that's 0.5. 2 minus 0.5 is this. So let me change color, and I'm going to put a box around that. These are part of my final answer. Okay, they asked us to solve for the final molarities of those two pieces, and I've now done that. Okay, let me just say again before we finish this problem, how did I know that that was going to be a plus sign? Like, how did I know that that wasn't minus? Because I looked from what happened from that initial condition to the equilibrium condition that was given to me in the problem. I could see that the product was increasing, which means that my reactants must have been decreasing. Okay. The last part of this problem, they asked us to calculate a value for the equilibrium constant. Okay, before we plug in any numbers, let's set up our expression. That's always a good idea. Okay, and remember, K means the equilibrium expression. So I want to plug in values from this line, the equilibrium line. Whoops. And now I have values to plug in there, so let's do it. Don't forget to keep those exponents. 1.5 squared times 1.25. And when we plug that into the calculator, we're going to get something in this neighborhood. For our value for K, remember K is typically expressed with no units. So there is our final answer. Okay, so in what I call type 1 is a problem where you'll be given initial conditions, and then you will be given one part of the reaction's final or equilibrium condition, and you'll be able to solve for X at that point. Okay, so I want you to try another problem very similar. It's actually the same reaction, the same balanced equation, but different values this time. Okay, and I want you to try this one on your own. Let me just give you one little hint before you pause the video and try it. I want you to look at the first sentence. Okay, as I said, this question is based off of the same balanced reaction we were just looking at. In the first sentence, you're given moles of SO2 and moles of SO3. You might be asking yourself, well, wait, where are the moles of oxygen? That's part of the reaction. If you are given a set of initial conditions and one of the parts of a chemical reaction is just not mentioned at all, mysteriously, in that first sentence where the initial conditions are given, guess what the initial value is for that piece? 0. This first sentence gives us an initial value of SO2 and SO3, but it doesn't say anything about initial conditions of oxygen. That must mean there is not any oxygen present initially. Okay, so pause the video. You guys take it from here. See if you can solve this one. All right, let's see how you did. So again, I was given all of the initial conditions, and then I was given one of the final conditions, which allowed me to then solve for a value for X. Okay, I took that value for X, and then I substituted it back in here and here, and that's where I came up with my final answers in the red boxes for the equilibrium constant, or equilibrium molarities, excuse me, of SO2 and SO3. Okay, I then plugged them in to the equilibrium expression, and I got my value for the equilibrium constant K. Okay, now this is not really tied to these reactions and these calculations, but I just wanted to point it out. The K value here in this problem we solved for was 4.32. In the one that I walked you through, it was the same reaction. We got 4.36. That's almost the same value. Remember, guys, it's the same reaction at the same temperature. The K value shouldn't be really any different. I'm just highlighting the fact once again that the only thing that can change the value of K, that equilibrium constant, is changing the temperature, which I did not do. Okay, I just wanted to reiterate that. So let's look at another problem. This is what I call type 2, which we're going to set up in the same way. You're just going to see that our unknown is going to be slightly in a different place. Okay, so this one says, for a synthesis of hydrofluoric acid from hydrogen and fluorine, 3 moles of hydrogen, 6 moles of fluorine, 12 moles of HF are mixed in a 3-liter flask. The equilibrium constant at this temperature is 115. Now this is a different setup. This time they're giving us the value for K. And the ultimate question says, calculate the equilibrium concentrations of all the components. So as we did before, the very first thing that I'm going to do is I'm going to write out the balanced equation. And I'm going to set up my ice table. And let's see what we can fill in. Okay. I stands for initial conditions. Okay, now it's not quite as simple and straightforward as the last one. We just have to do a little bit of mental math here. Molarity is moles divided by liters. So for hydrogen, that's going to be 1 molar. Okay, for fluorine, 6 moles divided by 3 liters. That's going to be 2 molar. And last but not least, hydrogen, or HF, 12 moles divided by 3 liters, so that's going to be 4 molar. Okay, I'm going to draw a line here. And this problem is different than the last ones because I am not given anything to put in these 3 positions. Okay, the last 2 problems we did, we were given the equilibrium conditions for one of the pieces, and then we could tell which direction it was shifting. We could solve for x. Well, we're not given that this time. Okay. However, we are given the value for K. Look at the information that I've written on the screen here. If I have all the initial conditions, can't I calculate Q, the reaction quotient? And the answer is yes, I can. Okay, which has the same expression as K does. And let's plug in these initial values. Let's get a number for Q. 4 squared is 16 divided by 2, so Q is equal to 8. How does that compare to the value for K? It is less than. Okay, and let's think back to the last lesson, guys. If Q is less than K, which direction is this going to shift? Okay, remember, a Q that is smaller than K, that means we don't have enough products. We need to make more. So we're going to shift in the direction that's going to create more products and consume some of those reactants. Okay, so I'm going to put a minus X there because reactants are going to be decreasing, products are going to be increasing. Okay, now let me just pause there for a moment. Let's kind of recap here. What makes this different from the last 2 problems we did? I did not have enough information to do this comparison here. Because the last 2 problems, we were not given the value for K. In this one, we are. This is the only way I can know, is this reaction going to shift in the forward direction or the reverse direction? Okay, so here's what we've got. 1 minus X, this is 2 minus X, and this is 4 plus 2X. Okay, now let me erase just a little bit of what I've done here before, because I don't think we need to see that. And now that I'm down on the equilibrium level, I'm going to change this to K. Now I don't have any numbers yet to plug in, okay? I haven't found a value for X at this point. So all I can do at this point is plug in these expressions. Okay, now, and we have a value for K. Now, you might be looking at this and saying, oh my gosh, to solve for X, oh, this is like my worst algebra nightmares come true. Okay, I am going to show you guys a quick way to do this, to solve a problem like this. First of all, let me say this, a problem like this, 99% chance, 99.9% chance, a problem like this will be on free response, where you have a calculator. Okay, so here's what I want to do, and I want to show you. I'm going to come over here. Okay, on your graphing calculator, okay, it doesn't matter what version you have. If you have the TI-89 or 84, it doesn't matter. They all have the same capability that I'm going to show you here. Could this be an algebra nightmare? Yes. Would it involve the quadratic equation? Yes. And that's icky, that's gross and yuck, and who wants to deal with that? There's a faster way. You can find that value for X by graphing it and finding the intersection. So I'm going to walk you through this. What I want you to do is go to y equals, and we're going to work this problem. So for y1, I want you to type in y1 equals 115, okay? Because that's what the K value was equal to, all right? In y2, we're going to plug in that entire equilibrium expression, all right? So I've got 4 plus 2x, parentheses around that, and then I've squared that. And then I have a set of parentheses around that entire numerator. Okay, if you can see that. And then let me scroll over. Okay, so that expression was 4 plus 2x squared divided by, let me move it over so you can see it, 1 minus x times 2 minus x. Okay, again, I put a set of parentheses around each one of those expressions, 1 minus x and 2 minus x, but I also put a set of parentheses around the entire denominator. You got to be real careful with your parentheses here. All right. From there, I just do zoom standard, zoom 6. That's what I do. Okay. And when it comes up, you're going to see a graph, and sometimes these graphs look really crazy. Sometimes they look normal, sometimes they don't. Okay. Now, if you'll notice, guys, on my screen here, I can't see the intersection point, and that's okay. You don't need to be able to see it, okay? We want the intersection point, so here's the last step. We're going to go second and then hit the trace button. We want the intersection, so I'm going to hit number 5. Now this is key. Are you listening? Hit number 5, intersect. Don't move the cursor. Don't move the cursor. It's going to say first curve, and you're just going to say enter. Second curve, enter. Guess, enter. Just hit enter, enter, enter. Don't move the cursor. I know that seems stupid. Why would it matter if you move the cursor? Just don't do it. You're less likely to get the wrong intersection point because there are going to be actually 2 intersection points. Don't ask me why. For whatever reason, if you don't move the cursor, you will always end up with the correct intersection point. I don't know why. Okay? But if you've done it right, ladies and gentlemen, my graph here, the intersection point, is showing x equals 0.7797 something, something, something. That's the correct value for x. Okay? So let's come back to the problem. Let me bring that back up. I've graphed correctly, hopefully, knock on wood. And I'm not going to round too much because this is not my final answer. 0.7797. Okay. Let's come back to the ultimate thing. What were we supposed to solve for the equilibrium molarities? All I have to do is take this value for x and plug them back in one at a time. So here's my final molarity of hydrogen. Let's do this. 1 minus 0.7797. I'll round to 2 sig figs. 0.22 molar. Fluorine is going to be 1.2 molar, or 1.22, it's fine. And then HF, the final one, let's do that. 0.7797 times 2 plus 4, we'll call that 5.6. Okay, so let me put a box around it. Here is my final answer. Okay, so let's just recap here. I couldn't solve this problem like the last ones because this problem did not give me an equilibrium value for one of the parts of the reaction. They did, however, give us the K value. Okay, the first thing we did was we found Q, we compared it to K, and that helped us determine the direction that this reaction would be shifting. Then we plugged in these expressions into the K for equal to the K value, and we graphed it. And I know you might be thinking, you know, that was a lot of work just to get X, but I promise you, the more and more you do this graphing routine, the faster you'll get at it, okay? If you do it enough times, it becomes like second nature to you to find that intersection value, all right? So this is the last thing that I want you to do, all right? This is a problem that is very similar. The only difference, ladies and gentlemen, is instead of being given initial molarities, you're going to do this problem exactly in the same format we just did the last one, except this time you're given pressures. But that's okay. Look, you're given a Kp value. You can put pressures into an ice table just like you can molarities. The process is exactly the same. All right, so pause your video, give it a try. All right, let's see how you did. And I know there's a lot going on this slide. All right, so let me talk you through it step by step. Okay, the first thing I did was I wrote down all of my initial conditions on that line. And then I came down here to calculate a value for Q, which I found to be equal to the number 5,000. We were given the value for K, okay, and let me be specific. That was a Kp value, Kp, okay, and I saw that the Q value was greater than Kp, which tells me our initial conditions, we have too many products. We need to get rid of some of those products, use some of them up. We need to create more reactants. So we're going to shift in the reverse direction, which helped me decide upon the signage there. Okay. I got my 3 expressions here and I plugged them now into a K expression. Here's my Kp value. I graphed it on my calculator, okay? Now, if you got a number other than that and you're having graphing issues, if those of you that are my students, you're welcome to come to me and we can work through your calculator issues and figure out what the problem is. 9 times out of 10, guys, the problem is that you've left off a set of parentheses somewhere when you're typing this whole expression into Y2, okay? But let's assume that you did get this value for X. You come back, you plug it in here, here, and here. and there are my final pressure values. Okay, so you can do an ice table problem with molarities. You can do them with pressures just as well. And you'll notice that this volume we were given here, totally extra information. We didn't even use it at all. So I know that was a lot, okay? It's a lot of calculating, it's a lot of math, okay? But I hope that you can embrace the method of using the ice table, because it really does keep your numbers organized, and it's a lot easier to see where your unknowns are, how are you going to solve for them. So it is a pattern that is very much accepted and encouraged on the AP exam, and I encourage you to use that method. Okay, of course, when you're solving for x using those complicated expressions, you can solve for x using a quadratic equation, but I personally don't like to do that, but you can do that. Some of you may have a program on your calculator called a quadratic solver that can solve it for you. Great. Okay, that I just prefer the graphing method. That's my thought. Okay, so I hope you all have learned a little something, and I look forward to seeing you next time.